Pen. Where is my pen? Here's my paper. Aha. We are ready to go. Math. A 200 gram piece of silver wire is wound into a coil and dropped into 270 milliliters of water in a calorimeter at 25 degrees Celsius. The final temperature of the water is measured at 51.4 degrees Celsius. Calculate the initial temperature of the silver wire. Assume heat transfer is complete. The specific heat of silver is this. For water, this. So I'm solving for a triangle T of the silver. So for silver, they give me a lot. The first thing I'm going to do is use water, though. So for water, I'm going to have Q equals SMAT. So Q equals 4.184 joules per gram degree Celsius times mass of water, 270 grams because of density. Water went from 25 to 51.4. So 51.4 minus 25 times 26.4 degrees Celsius. So with that, Q for water ends up being 22,865 joules. Then Q loss is Q gain. So therefore, the 22,865 joules that water gained is equal to C for metal, which is S, MAT, 235 joules per gram degree Celsius, times mass of the metal, which is 200 grams, times triangle T. So, let's solve that. 22865 divided by 0.235 divided by 200. So I am getting 486 degrees for triangle T. So the metal final temperature was 51, so 51.4 plus, it had to cool down, 486, which is my triangle T. So plus 51.4, I get 537.9 for Ti metal. Degrees Celsius. Okay. You want to determine the amount of energy in 50 grams serving your favorite corn chips and simple soda. Can calorimeter, your amazing chemistry teacher has made. Chips were placed into a metal weigh boat and set on fire beneath the soda can, weighing 75 grams of water. The water in the soda can started at 22.1, ended at 91.5. How much water was absorbed? How much heat was absorbed by the water? Q equals SMAT. Q equals 75 grams times 4.18 times your change in temperature, which is 91.5 minus 22.1, 69.4. So Q ends up being 21,757 joules. Assume a perfect transfer of heat. How much heat was given off by the chips? Well, negative 21,757 joules. Based on your data, how many food calories are there in chips? 1 calorie is 4.184 joules of energy. This is easy. So 21,757 joules times 4.184 joules in 1 kilocal. Oh, in 1 calorie. Sorry, in 1 calorie. So that gives me 5,200 calories, but they wanted kilocalories. So I'm going to divide that by 1,000, and you get 5.20 kilocalories. I don't think you'd see something like this. This is more CP Chem on the AP test, but easy. Nutrition label on chips state that 50-gram serving has 150 calories. Calculate your percent air. Well, that's going to be big because percent equals actual over lab divided by actual absolute value times 100. So that equals 150 minus 5.20 we just got divided by 150 times 100. It's going to be a big number. Yep. 96.5%. Odd. Identify sources of air. Well, heat was transferred because I'm way low elsewhere. Where could that elsewhere be? To the air, to the metal, to the weigh boat. There's lots of places that heat could have been transferred, but it wasn't transferred to the water. Okay, here we go. The term enthalpy is used to describe the heat exchange in a reaction. The symbol for enthalpy is delta H. To the right is a phase change diagram of a pure substance. Label with the following: solid, liquid, gas, melting, vaporization. So here is solid, and I'm going to add, this is, you have to do Q equals MC triangle T. This is a step E. This is melting, so you have to do stoich. This is liquid, so you have to do Q equals smat. I don't know why I keep going between the CP and this version. It's the same thing. This is going to be vaporizing, so that means I have to do stoich. And this is going to be a gas, so I have to do Q equals smat. This could also be condensing, going the other way. And this could also be freezing, going the other way. What is the approximate melting point of this substance? I don't know, 32 degrees Celsius. Boiling point, 61. There we go. Why does the temperature stay at 60 for so long? Well, this is important. The energy being 60, 61 put in is used to break the intermolecular forces that hold molecules in the liquid form, whatever those are. So that's why temperature doesn't change during a phase change. The amount of energy being put in is the same amount of energy being used to break the intermolecular forces. For water, that would be hydrogen bonds. For this substance, which state of matter has a higher specific heat, the solid or the liquid phase? How do I know? Well, it's obviously going to be the, let's see, let's be solid or liquid. It's going to be solid. How do I know that? Slope. The slope of my solid is lower than the slope of my liquid, which means it was harder to heat that solid up. So solid, because solid line has less slope than liquid. Label the locations in the graph where you'd use each equation to calculate the heat. Q equals MHF, so that would be here. Q equals MHV, so vaporization, that would be the stoich. Q equals MHV. Q equals MCAT, I already did that. MHF, mass times heat of fusion, mass times heat of vaporization, that's stoich. Oh man. Then there's a STEPI. So a 13.46 grams sample of ice at negative 8.7 is heated until steam at 100 degrees Celsius. Assuming no heat is lost to the surroundings, calculate the total heat kilojoules required to cause this change. Show your work. I am not going to do all of this, but I will show you the answer if you would like to do this on your own. So here is the work. You can pause if you want to do this on your own. So you have to do MCAT, STOIC, MCAT, STOIC, add them all up. We've done that before. And you would never have to do that on an AP test, but it's a good skill to have. Okay. Complete the following chart for each of the following physical processes: exo or endo, vaporizing. I need to put energy in, so that's endo. Condensing, I need to take energy out, that's exo. Freezing, take energy out. Melting, endo, put energy in. Positive delta H or negative? Positive, negative, negative, positive. Following information is about substance B. Complete the table. What is substance B? Substance B. Where was substance B? Oh, it's just a random substance. So to melt, it takes 25. To boil, it takes 58. Where are we coming up with this? Oh, duh. So to condense, it's the opposite of boiling. So this would be negative 58 kilojoules per mole. To freeze, it's going to be negative 25 kilojoules per mole, because I had to take those out. So condense, opposite of that. Freeze, opposite of melting. Okay, wow, I'm stupid. Next page. How does Q relate to delta H? Well, on all these graphs we've been drawing, my delta H technically is the enthalpy of reaction, which is really the change in potential energy. So the potential energy changes as the heat energy, Q, is transferred. So PE changes as Q, which is the heat, is transferred. So Q is the amount of heat released as the enthalpy changes going from reactants to products. That's pretty good. I kind of like how I said that. Potential energy changes as the Q, the heat, is transferred. That's good. I could go either way, exothermic or endothermic. The delta H of reaction is 3401. What does this mean? Write it out in your own words so that a first-year chemistry student could understand. Well, positive 3401 kilojoules per mole means it takes in / absorbs 3,401 kilojoules per mole of reaction. And remember, if you would have like 2 moles here, you'd have to divide this by 2 to figure out that out. So that's per 1 mole of reaction. So if one of these was 2 and it was asking you specifically about B, you'd have to divide it. Consider the following equation: how much heat Q would be absorbed or released by the decomposition of 10 grams of NaOH. Let's do some STOIC, baby. 10 grams NaOH times 39.997 grams of NaOH in 1 mole of NaOH. And I have, this is what I was talking about, for every 2 moles of NaOH, I have 1. Well, I guess I could say 1 mole of reaction, or I could have went straight to this. And every 1 mole of reaction is negative 568.98 kilojoules. So we're going to multiply that through, and you should end up with negative 71.9 0.1 kilojoules of heat released. Heat released should be a negative. Okay, we are making progress. I love this. For this topic, you will need a reference table of the average bond energies. So here's the link, or you can use your book. On the amino acid at the right, label the amount of energy it takes to break each bond. Hint, there are 9 bonds. So, or I could just give it to you. So this is 390. This is also going to be 390. This is going to be 293, 414, 414, 730. Shorter the length, stronger the strength. 464 and also 464. In the box to the right, draw the dot structure for each molecule in the following reaction. CCl4, C, Cl, 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 Cl. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Plus 2 waters. H, O, 1, 2, 3, 4. H, H, O, 1, 2, 3, 4. H. Yields CO2. We know that's double bonded. 1, 2, 3, 4. 1, 2, 3, 4. Plus HCl. So HCl. 1, 2, 3, 4, 5, 6. 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 Okay. How much energy is required to release to break the bonds of the reactants? Well, it's going to be required to break. So I have to break 4 of these Cl. So I have 4 Cl to C. Plus, I also have to break 4 of my HO. 4 of my HO. So that's going to be 4 times, you'd have to look this up in your book, 276 plus 4 times 464. So reactants equals 2960. How much is released to form the bonds of the products? So I form 2 C double bonds. So I have 2 C double O's being formed. Plus I have 4 HCl's. So that's going to be 2 times 730 plus 4 times 431. You have to look that up in your book or using this. So my products are 3184. We know that bond energies are reactants minus products. So it's going to be 2960 minus 3184, which gives us negative 1224 kilojoules. Therefore, this reaction is exothermic. Circle the energy profile at the right that most closely matches the change in enthalpy of the above reaction. Has to be this one, because my products have to end lower than my reactants. That is exothermic. How close are we? 1, 2, 3. So close. I don't know if I'm going to have time to finish this right now. We'll see. There might have to be a little mini part 3. Use the large delta HF in the left column to label each part of the symbol. Oh. Here we go. This is change. H is enthalpy. The little 0 is standard conditions. And F is just formation. What are the standard conditions assumed for standard enthalpy calculations? 298 Kelvin, or 25 degrees Celsius, and 1 atm. Which method of calculated change in enthalpy of reaction is more accurate? Using enthalpy of formation or bond enthalpy? Explain why. Well, it's going to be enthalpy of formation. Here's why. I don't think we've talked about this, but the bond energies are averages. So the bond energies are more estimates and averages, but the enthalpy of formation is exact. So that's why. Enthalpy of formation. Bond energies are more of an average. Use the information given in the table, calculate the enthalpy of reaction, show your work in the box below. So we know that enthalpy is products minus reactants. So delta H equals sum of, is this balanced? I don't know if this is balanced. I have 3 H's, 7. This is not balanced. I would have to put a 2 here. It's kind of annoying. A 6 here. A 2 here. 2 here. Now it's balanced. I don't know why they didn't just balance that for us. That's okay. So sum of 2 HCN times, HCN is 135.1 plus 6 H2O, 6 moles H2O times negative 242. That is my products minus sum, my reactants. Oh wait, I forgot CH4. Whoops. Plus, I have 2 CH4 times negative 75. There we go, that's end bracket. So that minus, for my products, I have, or for my reactants, I have 2 moles of NH3 times negative 46 plus 3 moles of O2 times 0. Add that all up, and your delta H you should end up with is negative 939.8 kilojoules per mole. Does this reaction absorb or release energy? Release. How do I know? It's exothermic. It's negative. Okay. Rewrite the following reactions so it is reversed. Okay, that's weird. So Mg OH2, which is a solid, is going to give me MgO, which is a solid, plus H2O, which is a liquid, which means my delta H is now positive 37 kilojoules. Rewrite the following equation so it's halved. Okay. 1/2, 3/2, 1, 3/2 divided by 2. So that is negative 617.5 kilojoules. That's just showing if you multiply this by 2, you multiply this by 2. Divide by 2, divide by 2. Blows hypothetical reaction. Table shows all the reactions that go into the overall reaction above. Determine the net enthalpy for the reaction. This is Hess's law, which is kind of my favorite. So this is where you have to figure out all the reactions, cancel them out. I'm not going to work through that whole thing. I'm just going to give you the answers. So what did I have to do? I needed to get ACD2 on the right. So reaction 4, I left. I had to get B2D2 on the right. So for that one, my B2D2 was reaction 5, so I had to flip that to get B2D2 on the right. So I flipped that one. To get AB2 on the left, I had to flip reaction 1. So that's why that became a positive. And the 2C2D on the left was here. And I already flipped that one. And then I'm going to use the other ones just to cancel out. So I need a 2C2D. So that one plus that one gives me the 2. If you want to work that out, you can, but that's a Hess's law, and you should end up with 549.9 kilojoules. I just don't want this to be super long for you guys to go through. The owner of an orange grove is facing a night with abnormally low temperature. She decides to spray his trees with water. Why does spraying the trees with water before frost help to protect the fruit from freezing? Well, water releases heat when freezing. It's exothermic. Therefore, that heat goes into the fruit. Oops, I just gave that away. Exothermic. So that means the heat is going into the fruit. Circle around orange is the layer of water undergoing phase change. Use arrows to show heat exchange occurring between the freezing process. So heat is going from the freezing water to the orange. It's also releasing heat to the air, really. It's really going both ways. But the main, it's more is going into the orange. A soccer player twists their ankle during a game. The trainer grabs an emergency ice pack. This pack requires a snapping tube inside and then shaking to mix 2 chemicals, making the bag very cold. The bag is applied to the ankle. Explain the direction of heat. So this is endothermic. So heat. Because heat is going from the ankle to the bag. Because heat only flows from hot to cold. Heat from the air would also be going to the bag, but we're really just talking about the ankle. And that is Unit 6. Yahtzee.